Makes sense.
Exactly.
Yeah, make like $1.05. So yeah, that adds up though.
Hello and welcome back to Calculus2. We are, yes, Calc2, exactly. We all miss Sharif now, right? Maybe if everyone's free, come back. Maybe he comes back next class. I don't know. Anyway, partial fraction decomposition. So, partial fractions are something that you might have studied in a pre-calculus course, and it's this algebraic technique that you use to break a rational function into sum of two rational functions. So I'm going to give you the example of what that means. So if you have, let's say, 2 over x minus 3 plus 1 over x plus 1, right? If you have this in algebra, you would find the common denominator and you would add these into a single fraction. So the denominator would be multiplied into, well, first write x minus 3, x plus 1, and the numerator would be 2x plus 2 plus x minus 3. So the total for this would be 3x minus 1 divided by x squared minus 2x minus 3. So that would be the answer. So this is something that you do in algebra, right? You have two rational expressions and you add them by figuring out the common denominator and then working on the numerator to simplify as much as you can. And that's the end of the story. Now, what is partial fraction decomposition? Partial fraction decomposition is, so partial fraction decomposition, PFD, is going to take 3x minus 1 divided by x squared minus 2x minus 3 and gets you into 2 over x minus 3 plus 1 over x plus 1. You see, there is no way to integrate, right? There's no way to integrate 3x minus 1 over x squared minus 2x minus 3 dx. U substitution doesn't work. Trig substitution, it's not gonna work most likely. Or actually, maybe it would if you complete the square and you hope, you know. Maybe completing the square over here would work, but as soon as if I had x cubed in the bottom, it's just shot, right? So none of the techniques that we learned so far would work. But if you know how to do the partial fraction decomposition, this integral becomes 2 times integral of dx over x minus 3 plus the integral of 1 over x plus 1, dx over, right? Because you remember that you can break the integral into 2 integrals if you have additional multiple terms. And then, now it's easy, right? Each one of these is ln. So 2 ln of x minus 3 in absolute value plus ln of x plus 1 plus c, and you're done. So this procedure that we are going to talk about, the partial fraction decomposition, is necessary because it would make some of these problems that we can't solve otherwise possible for us to do. So now, what is the partial fraction decomposition? Well, we start with 3x minus 1 divided by x squared minus 2x minus 3. So, partial fraction decomposition. What is it all about? Well, we start by, number 1, factoring. Denominator. We have to factor denominator because that is where we do the split. So when I factor denominator, I will come up with x minus 3, x plus 1, and you still have 3x minus 1. So the step number 1 is factoring. And then step number 2 is split. So now each of these factors will get its own fraction with a plus in between. And then here is in red, list 4 numerators. So this is actually what you have to memorize. There are 4 cases that you will have to consider. If your denominator is x plus minus a value a, then you will put constant on top. If your denominator is x plus minus a squared, then you will have a of x plus minus a squared plus b over x plus minus a. If you have denominator to be ax squared plus bx plus c, so it's a quadratic function that cannot be broken any further, factored, then your setup over here is ax plus b over ax squared plus bx plus c. And finally, if you have the repeated, so ax squared plus bx plus c squared, then that will be ax plus b divided by ax squared plus bx plus c squared plus cx plus d divided by ax squared plus bx plus c. So these are the 4 situations that you have to memorize if you have a linear term, which also includes when it's a single x, right? Because that will be single x plus 0. If you have a linear term, then you have constant over those linear terms. If the linear term is squared, then your setup is this one, and you have the quadratics, those are the setups. Where are you going to find these denominators? When you factor, you can get any one of these. Let's say you have to factor x cubed minus x. If your problem was x cubed minus x, that would factor into x squared minus 1, and then this x squared minus 1 still factors into x minus 1, x plus 1. You see? So now that one has 3 factors. They are all basic linear terms, so all of those fall under the first one. So your setup would be a over x plus b over x minus 1 plus c over x plus 1. Right? You would have 3 of these because that's linear, that's linear, that's linear. Yes?
For the capital letters, we actually just put those in.
Yes. Now, if this was x cubed plus, right, then in that case you cannot factor any further. Then you would have, for x, you use the first row. For the second one, you are using third row because that's unbreakable quadratic. So your setup would be a plus bx plus c, right? Because you just keep using the next letter in line. We'll obviously practice this much more, but I needed to make sure that you guys understand that this is what you must know if you want to set these up and be able to solve these integrals. So we start with, to do partial fraction decomposition, step number 1 is to factor denominator, and that will tell us all the different things that we need from the list. Once you are done with that, then you split into each one, and now we are using A and B because both are linear in the denominator. If you have a quadratic, you will be using linear on top. So now, once I have that, I go and I solve it. Because now I can add those, right, do the algebra, and then I'm going to compare whatever I have here with whatever the original one is and figure out what A and B are. Which we already know what they are because we started by knowing, but we want to get those. So now, where am I in the problem? I am at 3x minus 1 over x squared minus 3x minus 1, I guess? No, minus 2x minus 3, minus 2x 3, is equal to a over x minus 3 plus b over x plus 1. So this is where we are right now. The only thing that I can do is add fractions on the right-hand side. The denominator will multiply obviously into x squared minus 2x minus 3. And the numerator becomes ax plus a plus bx minus 3b. And now I compare. So I have 3x minus 1 is equal to ax plus a plus bx minus 3b. Observe that I'm not worrying about denominators because denominators are the same. If these two fractions are to be the same, their numerators must be the same. Denominators are already the same, so we don't have to worry about denominators ever. It's just that the numerators have to equal. Now observe what you have. On the left-hand side, you have a pile of x's and a pile of numbers. So arrange your right-hand side in that fashion. So I have 3x minus 1 is equal to a plus b all times x, right? That's when I combine this with that. They're both having x. You factor out x, you're left with a plus b. So you are putting all of your x's on a pile, and then plus a minus 3b. That goes on a pile as well. So now, color coding. Coefficient of x has to be the same as the coefficient of x, and the constant term has to be the same as the constant term. This is where you get your equations. So your red equation says that 3 is equal to a plus b, and your blue equation says that negative 1 is equal to a minus 3b. This is a system of equations. Sometimes this is 2 by 2 system, sometimes it's 3 by 3, sometimes it's 6 by 6. Depends on how many of those capital A, B, C, D's you have. You have to find all of them. So if you have A, B, C, D, that will work out to be 4 equations with 4 unknowns, and then you spend time figuring it out. Right now, this system is easy. I have that a plus b is equal to 3 and a minus 3b is equal to negative 1. Simple subtraction of these equations as equation 1 minus equation 2 will give us, right, a dies. You will get 4b is equal to 4, from where we got that b is equal to 1. If b is equal to 1, then a plus 1 is 3, then a is equal to 2. Didn't we have 2 and 1 to begin with? Oh yeah, we did have 2 and 1 to begin with as our a and b. So now you plug those in where they belong. So a is 2 over x minus 3 plus 1 over x plus 1. And that's exactly what we were looking for. See that? There they are, right there. You can practice this at home by writing any of these rational functions, multiplying them and adding them out, right, into this, and then unleash the partial fraction decomposition to practice. You don't even need the textbook and the problems or homework. You can just make up your own, just like I did. Let's see if I can find more examples. So we are technically learning the pre-calculus now. because the calculus part, you just take the integral, and the integral is either going to be basic or ln or inverse tangent, right? Those are the three choices that you're going to end up at the end with. So, yeah. What do I need now? Come up with different examples. So how about we have, so we're only worrying about, nah, let's not worry about cell, let's do the whole thing. I should work it out on the side, so I'm not, whatever. Let's just do this. So we have 3x plus 5 divided by x minus 3 squared. So let's say this is something that you are supposed to work the partial fraction for. Probably I'm going to regret this, but because I put in whatever, but that's okay. Such is life. All right, so what do I have? Well, I have a linear term. Linear term is just a over x, right? Because x is linear term, so it gets a constant. Then I have a repeated linear. If you remember in my red list, repeated linear has also a constant on top, but it actually has two terms. So this is the appropriate setup for the problem. We have a linear term that gets the constant above, and then we have a repeated linear. So for the repeated linear, I have to go repeated linear and then just a linear, and each one gets a constant. Let me scroll up to our red rules. There we go. Red rules. Here is your repeated linear. Repeated linear has a setup as a constant over repeated plus a constant over just a linear. So once you have that set up, now it's your job to add everything on the right-hand side and compare the numerators, right? That will tell you the equations and the numbers, right? Equations that you need to calculate A, B, C. You have A, B, C. Most likely you will have to solve 3 by 3 system in this case because you have 3 unknowns, right? A, B, and C. Now in some cases, right, stuff works out nicely and you get to eliminate one of the variables quickly, but most of the time it will not be nice. So what you do is you have to crank the calculations here. Now, the way we do this is we play the game of what's missing, right, for common denominator, because this is your common denominator. So what's missing in these equations? Well, this one is missing x minus 3 squared. This one is missing x, and this one is missing x times x minus 3. So when you think about this, right, this is what each one of these is missing to create common denominator. So now, since denominators are the same, we can just multiply both sides by that denominator. Denominators go away. And I have 3x plus 5 is equal to, and now I have to work all of these out. So when I FOIL x minus 3 squared, I get ax squared minus 6ax, that's the middle term, plus 9a. And then we have plus bx, that was easy. And finally plus cx squared minus 3cx. We have to group them again, right? X squares with x squares and x's with x's and constants with constants. So 3x plus 5 is equal to, now x squares, I have a plus c times x squared. So a plus c are the coefficients of x squared when you factor out x squared. Now for x, I have negative 6a, I have b, and I have 3c. So plus, open parenthesis, negative 6a plus b from this term, and then minus 3c from that term, and that's times x. And the only thing that is left is a constant term. Now that constant term over here, the only constant term is 9a, right? So now we get to set up equations. Again, color coding over here. Well, I don't have anything for x squared. So this thing has to be equal to 0 because there is no x squared term on the left. But the rest I can do. I can say 3 is equal to this mess over here. And let's say green, 5 is equal to 9a. Oh, we are lucky that 9a right there. Right, we don't have to do 3 by 3 system. So what do I have? I have a plus c is 0. I have negative 6a plus b minus 3c is equal to 3. And finally, 9a is equal to 5. Whew, I like that equation right there. A is 5 over 9. As soon as a is 5 over 9, then c must be negative 5 over 9 because they have to add to 0 because of the first equation. And now I have my a, I have c, so I can find b easily from the middle equation. Negative 6 times 5 over 9 plus b minus 3 times negative 5 over 9 is equal to 3. The only variable there is b, so we just have to work on that. These guys cancel, so that's negative 10 thirds plus b plus 5 thirds equals to 3. And then this is already single b, so b is equal to 3 plus 5 thirds, because 5 minus 10 is negative 5, and then goes to the other side as positive 5 thirds. So this is equal to 4 and 2 thirds, which is 14 thirds. And there they are. I'm done. So my partial fraction decomposition for this problem here is equal to a, which is 9/5 over x, plus b times x. B is 14 thirds, x plus c, which is minus 9 over 5, everything divided by x minus 3 squared. So now this is this 5 would go in denominator. Actually, it's better if you leave it there, but how about 9/5 times 1 over x plus over here multiply top and bottom by 15 to get rid of the double fraction. So if you multiply top and bottom by 15, you get on the denominator 15x minus 3. In the numerator times 15, 5 times what is 70x minus 27. There it is. Now you would do individual integrals on each one of these, and then good luck with the rest. Right? Partial fraction decomposition. Do we have time? Oh, we have time for more. Yes.
How do we have 9 over 5 over 9 over 9 over 5 over x?
Like, how did you get those parts?
Get to which part?
Those two. Oh wait, yeah, it's like the last part.
Did you have a third part?
But yeah, no, up one.
Oh yeah, we did have a third.
So you do plug back into.
No, wait, hold on.
Yeah, wait, do you plug back into those equations?
Oh yeah, I used the wrong stuff.
Bada boom. Yeah.
Okay, so now it feels like sorry, x minus 3 squared, and this was b, so that's 14/3. Yeah, please erase. Plus negative 9 over 5 over x minus 3. Yeah, this is all wrong. So now we have.
You plug it back into the equation we made.
Yeah, 9 over 5 times 1 over x plus 14/3 times 1 over x minus 3 squared minus 9 over 5, 1 over x minus 3. There we go, much better. Now, guys, this is not integral done. This is just partial fraction decomposition. Now you integrate each one of these separately. The first one, easy, ln. Second one, easy, u sub. Third one, easy, ln plus c at the end.
Oh yeah.
Right?
I think the second one, we're going to have to do like something not.
Well, as I said, you only have the choice between ln, u sub, and the inverse tangent. That's it.
Not three.
Nah. I mean, I could possibly create a problem.
What do you think?
Exactly. Do I?
I took like a weird version of Calculus in high school, and this is like the last thing we learned. And there's like 30 points on our last test, and I couldn't know if I did it.
I would say I could relate, but I can't.
No, I was terrible at Calculus.
Well, enjoy your victories now.
Yeah.
I love how the textbook gives you the titles for each one of the simple linear factors, simple irreducible quadratic factors, right? They toss in this word simple, as it's like no sweat broken at all. It's just, it's very simple. One page of tedious calculation aside, yeah, simple.
To make you feel bad when you can't do it.
Yeah, right? You just go and they say, you're looking at this and I say, how simple am I if I can't figure out a simple, right? Yeah, that's that part. But
could you scroll back up to the red text for the column just before?
These ones?
Yeah.
Take the picture quickly.
Oh, no, the next. Just under that red text. I guess the next column.
This one?
No.
Oh, you mean up? There's nothing else. This is the only red stuff, and then you have this. You said red.
Yeah, the midsection between this and the red.
This?
Yeah.
All right. Scroll on the stream over there. You're holding up the progress. All right. So what do we have? Let's do one of these simple, irreducible quadratic factors. That sounds cool. Problem 44. Now let's do, the whole spiel over here. So problem 44, we have integral of x squared plus 3x plus 2 divided by x, open parenthesis, x squared plus 2x plus 2, close parenthesis, and then dx. Well, it's already set for the partial fraction decomposition because it's already factored, and they told you that the quadratic piece is unfactorable, irreducible. So what we have is the first one is x, so a over x, that's the quadratic, that's a linear, so it just gets a constant. And then you have dx, let's put parentheses, plus, and now it's a quadratic, so it's going to be bx plus c, divided by x squared plus 2x plus 2, dx. And now we are going to solve use the cross multiply method. So when you cross multiply, what do you get? You get bx squared plus cx plus ax squared plus 2ax plus 2a. When you do cross multiply, divided by x squared plus 2x plus 2, all of that dx. So all I did is cross multiply. I only have two fractions there, so when you have two fractions it's easy, you just cross multiply. So a multiplies into all three of these, and then x multiplies, no coughing, into these guys over here. So now we go and we do the comparison. So I have to compare x squared plus 3x plus 2 to bx squared plus cx plus ax squared plus 2ax plus 2a. All right, we can do this. X squared plus 3x plus 2 is equal to, now I have a plus b as I factor out x squared. And then I have 2a plus c when I factor out x, and then I have plus 2a at the end. So that's gone, that's gone, that's gone. Okay, perfect. Now, color code for equations. The coefficient of x squared has to be equal to a plus b, so a plus b is equal to what?
I might have missed it, but the step under the integral, what happened to that x that was outside of the quadratic term?
This x?
Yeah.
Nothing. Why? What happened to it?
How come it's not in the next step?
The next step is only numerators. It's because denominators are the same, so it's this equal to this. All right, so now let's go. What's the coefficient of x squared? 1. Now, blue. 3 equals to this, so 2a plus c is equal to 3. And finally, green. 2 is equal to 2a. Oh, well, that's nice. A is 1. And if a is 1, that propagates through all of the other ones quickly, giving us that b is 0, because 1 plus 0 is 1, and immediately giving us that c is 1 as well, because 2a, if a is 1, that's 2 plus c, is equal to 3 when it goes to the other side. It's that. So what do I have? I have integral of 1 over x plus, what was my bx plus c? So b, which is 0, x plus c, which is 1, divided by x squared plus 2x plus 2, and everything dx. So now we can split this into two separate integrals. I have 1 over dx over x plus another integral that it's integral of dx over x squared plus 2x plus 2. The first one is easy. It's just ln absolute x plus, and now what do we do here? Maybe later, but now you see that you have to do the trig sub. Even though we said there's no trig sub, there's a problem with the trig sub. Nice. I know, right? This is awesome. I love it. You have to do completing the square and then crank the trig sub on this problem. I know, right? So let's go green. Yeah, you did sign up for this. Per problem. X squared plus 2x plus 1 plus 1. I split this way. X plus 2, no, x plus 1 squared plus 1. Perfect. So my integral turns into the integral of dx divided by x plus 1 squared plus 1. And yeah, there's your inverse tangent you wanted. This is inverse tangent of x plus 1. So the answer over here is ln absolute x plus inverse tangent of 1 over, no, of x plus 1 plus c. Now, if you don't know that this is inverse tangent, then you will have to go and crank your trig sub, and so it's not clear that it's inverse tangent when it's in this form, but it is clear that it's inverse tangent when it's in that form. Because the inverse tangent inverse tangent, if you take the derivative of inverse tangent of x, you get 1 over 1 plus x squared. If you integrate 1 over 1 plus x squared dx, you get inverse tangent of x plus c. So I hope you see that the green form over here is identical to that form over there. Except you don't have x, you have x plus 1. But that's why in the answer I have x plus 1 rather than x that was there. So that should make sense. So we saved a lot. Now, what is going to be beneficial for some of you, or all of you, is to go and actually do the green integral using trig sub, to practice trig sub, and also to see that that's going to be an answer. Partial fraction decomposition, done.
Is it harder? Like current stuff?